Hello Math 1100 students. Previously in week 12 we studied exponential and logarithmic functions. Now let's use those to solve exponential and logarithmic equations. First, let's begin with some reviews. Here we go. This is the way we define exponential functions. A to the x power where the base a is positive real number. In that case, we have to have a one-to-one function. When a is equal to 1, then 1 to any power, that's just constantly 1, so a is not equal to 1. In that case, we have to have a one-to-one function, so it's invertible. The inverse function is called a logarithmic function. And therefore, all the properties of inverse functions apply, like domain of the inverse function is the same as the range of the original function, and the range of the inverse function is the same as the domain of the original function. Original and inverse functions cancel each other out whenever they come one after another. And here are a couple of applications of those cancellations. And then here are the graphs. Far more important case is when a is greater than 1 like this. Exponential function increases from 0 to positive infinity. As a matter of fact, not exactly 0. It reaches 0 when x goes to negative infinity. So the range is actually 0 to infinity with open bracket. Open parenthesis, no bracket, open parenthesis. Now for the logarithmic functions, when x is 0, logarithm is undefined, so we have vertical asymptote, and the domain is 0 to infinity, open parentheses. Symmetric with respect to the diagonal y equals to x. That's clear because they are inverse of each other. Now when a is less than 1, this case is far less important, so let's not worry about this. Next, exponential and logarithmic rules. Exponent rules, this is something we had been studying for, well, quite a while, as a matter of fact, all the way back from elementary algebra, maybe even before that. 0 power is 1, 1 power is itself, negative first power is reciprocal, and 1 to any power is 1. And then the standard rules. When bases are the same a, then multiplication becomes adding up the power, division becomes subtracting the power, and power of power, we have multiplying the power. Two different bases, but exponents are the same, then we have distribution. Okay, so much for exponent rules, and we have these 3 logarithmic rules, and the first is the cancellation rules, and that's because these are inverse of each other. Exponential and logarithm cancel each other out, so this part and that part cancel, we have just x, and log and exponential cancel out, these cancel out, and we have just x. And those two are important. Cancellation given by inverse functions. And these two are applications actually. So what is log a of a? That's the same as log base a of a to the first power. So cancel out and we have 1. Just using this rule here. Another example is here. Log a of 1. What is it? Log a of a to the 0 power. So again, this rule applies. Cancel out and we get 0. Now here are standard rules. Now logarithm changes multiplication to addition, division to subtraction, and power to coefficient. Okay, power comes out as coefficient like this, and that power does not have to be integer power. So whenever we have fraction over here as k power, that means radical. So radical computation becomes coefficient computation. So the computationally it became a lot better. And well, multiplication becomes addition, that's a step up. Division becomes subtraction, that's 10 steps up. And then radical becoming coefficient computation, that's 100 steps up basically. Now remember, we need 2 different operations. If you have same operations, then something is wrong. You see, all these are wrong. Plus remains as plus. no good. Multiplication remains as multiplication. Again, no good. We have to have two different operations. Addition becomes, no, the other way around. Multiplication becomes addition, division becomes subtraction, and power becomes coefficient. We're going to talk about those derivations and proofs in separate optional videos. Instead, let's just go on. Now, change of base rules. And these are important for computation. If you have, say, any number, say pi to 7th power, that's not too bad. Any integer power is just repeated multiplication. So pi to square root of 2 power, for example. In that case, how are you going to do that? Change it to exponential, natural exponential like this, and then you can use calculator for that. Your calculator will support natural exponential and natural logarithm. Same for arbitrary logarithm. Log base a can be changed into natural log over natural log like this. So you can use your calculator that supports natural logarithm to calculate any kind of logarithm or any kind of exponential. Okay, so much for all those reviews, and let's go to some example problems. The first type of example problem is consolidation, combining all those into a single logarithm. Here we have two logarithms, put them together into one logarithm. We have three logarithms here, put them all together into one natural logarithm. We have four logarithms here, again put them all together to one logarithm, those kind of things. Now the second example here are going backward. If you have one complicated logarithm, you can expand those out into several simpler logarithms. In this case, you can decompose into 3 logarithms. In this case, you can decompose into 4 logarithms. Let's go to this. Now, how do you handle this kind of problem? Usually, you have to apply the log rule number 3 first. This one first. And then we're going to use addition and the subtraction, those two together at the same time, simultaneously. So this one first, and then these two simultaneously. Okay, let's go. So we have natural logarithm here. Okay, and then this is natural log of u to the 3rd power plus natural log of v to the 2nd power, isn't it? I just used the log rule number 3, the standard log rule number 3 backward. Coefficient goes up the power, like this. Coefficient goes up the power, like that. And then we have two logarithms added together, so addition becomes multiplication. Log of u to the 3rd power times v to the 2nd power. And that completes the simplification. I don't know whether this is called simplification because it's quite arguable whether this is simpler or that's simpler. But it's a consolidation into a single logarithm. Makes sense? Here's the answer key. Okay, how about the next problem here? Okay, we can use rule number 3 before anything. So negative log of 2u, okay, that was there before. And then minus log of v to the 3rd power. And then plus, log of w to the, what did I do? I accidentally put caps lock here. So 3rd power is going up, so we have 6th power there. Does it make sense? So that becomes this. Now, and then we can apply the first and second logarithm. The third rule we did, and first and second log rules. How do we do that? It's far more convenient to use them all together in a single step. You can do it pair by pair. Take one pair, do it, and then another pair, do it, and then another pair, do it. and take those into 3-step, 4 steps, too inconvenient. Much better to do all those in a single step like this. Addition is multiplication, so that goes to the numerator. Subtraction is division, so that goes to the denominator. So natural logarithm of w to the 6th power, that has plus, so that goes to the numerator. And then the others, 2u, and then v cubed. And that's the end of the problem. So numerator, that means addition, plus. And denominator here, that means division. So that's subtraction, like this. That's one way to do it, and that's the way I like to do. Let me put it as solution 1. Here's solution 2. A lot of people do it this way as well. Not my favorite way, but it works out too. So log of 2u to the negative 1st power plus 3, no, log of v to the negative 3rd power plus log of w of, so 3 goes up, 6th power. So what do we have? We simply have all the addition. So we can simply multiply all those. So natural log of w to the 6th power, and let's just start from the left hand side. Negative 2u to the negative 1st power, v to the negative 3rd power, w to the 6th power. And well, you can stop here because the problem asks you to express this into one logarithm, did not ask you to simplify with only positive powers only. So you can stop there, but it's customary to go one step further. Logarithm of w to the 6th power, and then negative powers are all going to denominator, 2u, v to the 3rd power, like this. And then of course we have the same answer as before. Which type do you like better? My favorite way is to do it this way, but the second way works out too. I'm not going to prevent you from doing one or the other, but I'm running my class, so I'm going to stick to my favorite method, just the first method. Well, we'll have time to do only one more problem here, so let's use the first method. Ready? Okay, log of u squared minus log of v to the negative 1/2 power. Oh, wait a minute, I decided not to do it. I'm doing the first method. So 1/2 power, that means square root of v. Log of, now 3 is going up, so 6 squared minus log of 2x to the 2nd power. All right? Now put all those into same logarithm, single logarithm. Now addition becomes multiplication, so those are the numerators. And then subtraction becomes division, so those are the denominators. So let's deal with additions first. U squared, x to the 6th powers. Okay, and then how about the denominator? Square root of v, and then 2x to the 2nd power. Okay, all right. And you can stop here, but looks like a little bit more simplification is in order because we have x in the numerator and another x in the denominator. So it looks like this is 2 squared, so I'm going to get 4. And then you have x squared here, we have 6th power here, so we're going to come down to the 4th power. And that'll complete the problem. Let's check the answer. Yes, that's how we do it. Here I left it as 1/2 power, but square root is just fine.